We will build a great wall along the southern border.
When Donald Trump became president of the United States, he surprised the world. But among all the debates and arguments, there was one huge project he pushed that got the whole country talking. A massive border wall almost 3,200 kilometers long, about the distance across the U.S., from the Pacific Ocean in California to the Atlantic coast in North Carolina. The wall uses tall steel posts nearly 30 feet high, set deep in concrete. All of this makes the border feel like an almost unbreakable barrier. But why is this wall so important? And how did the U.S. manage to build such a huge steel structure in such a tough and dangerous environment? Let's take a closer look and discover the secrets behind it. For decades, the U.S. southern border was like a door left slightly open. According to U.S. Customs and Border Protection, in 2019 alone, border agents recorded more than 851,000 illegal crossing attempts. To deal with the problem, the U.S. government started building the first border fences in the 1990s under President Bill Clinton. Later, George W. Bush and Barack Obama continued to expand the system, but those fences were only a few meters high and fairly easy to climb or cut through. By 2016, Donald Trump turned the idea of the wall into a major part of his political message.
Build that wall, build that wall, build that wall.
He wanted to build a huge, strong barrier stretching thousands of miles. At first, he pushed for a solid concrete wall. But the Department of Homeland Security rejected the plan, saying it would stop patrol agents from seeing what was happening on the other side. In the end, the final design used tall steel posts, known as bollards, strong, high, and see-through. This became the main model for the border wall we see today. The first step in building the border wall was surveying the land. The planned wall stretches almost 1,930 miles along the U.S.-Mexico border, crossing many different types of terrain. Soft sandy desert that can sink, wet clay areas near the Rio Grande River, and hard rocky mountains in Arizona and California that feel like natural concrete. Engineers had to measure elevation, drill soil samples, check how stable the ground was, and calculate how deep the foundation needed to be in each location. This survey step was critical because it determined the entire foundation design and structure of the wall that followed. To install those steel posts that stand almost 30 feet tall in the desert, the first major step was digging the foundation. It may sound simple, but this was one of the most time-consuming and labor-heavy parts of the entire project. Construction crews had to dig a long, continuous trench about 24-32 inches wide and 6 to 10 feet deep, strong enough to hold each steel post against high winds and possible damage. In areas with soft sand, excavators and bulldozers could dig the trench fairly easily. However, most of the border runs through hard, rocky terrain where granite and sedimentary rock sit right under the surface. In these places, regular digging machines were useless. Crews had to use hydraulic rock breakers attached to heavy excavators, hammering and cracking the rock non-stop to remove large chunks from the ground. After the trench was roughly shaped, a specialized trenching machine called a trencher stepped in. These high-power machines usually run on diesel engines with 250-400 horsepower, allowing them to cut through hard ground at a steady speed. Once the excavators created the first rough trench, the trencher moved in to cut deeper and straighten the walls. At the same time, it crushed any remaining soil and rock, leaving the bottom flat and even. A conveyor system at the back constantly carried the loose material out of the trench, keeping it clean and ready for concrete. Because a trencher can cut continuously with high accuracy, it can handle hundreds of meters of trench per day, greatly speeding up the construction process. After the trench was dug and the bottom was leveled, the construction crew began installing the reinforcing steel frame. This frame is made of vertical steel bars and horizontal ties, forming a long steel cage running along the trench. Right after the rebar frame is set in place, a reinforced concrete layer about 10-20 centimeters, 4-8 inches, thick is poured over it. This creates a flat, stable, and strong base where the steel panels can be placed without sinking or tilting. When the concrete bonds tightly with the steel cage inside, it forms a solid, continuous foundation block. This greatly increases the wall's resistance to pulling forces and twisting, especially in the desert, where strong winds can put a lot of pressure on the structure. After the foundation was ready, the construction site moved into a very important stage, bringing in and preparing the steel bollard posts, the main parts of the wall. These posts are actually hollow steel tubes, either square or round, about 26 tall, with a thickness of 10 millimeters. The hollow design helps reduce weight and makes transportation easier, and it also allows concrete to be poured inside later to make the post stronger if needed. Each steel post can weigh between 250 and 400 kilograms, so they are transported from the factory to the site on heavy-duty trucks. The posts are stacked in layers and secured with steel straps to keep them from shifting during the trip. When they arrive, mobile cranes or truck-mounted cranes carefully lift each bundle off the truck and place it in a storage area, avoiding impacts that could bend or damage the steel. Right outside the work zone, a temporary fabrication area is set up. Here, workers use high-power welding machines to connect the posts into panels, with each panel usually made of 4x6 posts depending on the wall width. Welding them into sections makes installation much faster. Instead of lifting one post at a time, a crane can lift an entire panel and place it directly into the trench. This process requires very high accuracy. Even a small mistake of a few millimeters at the base or at the welds can cause the whole panel to lean, making alignment and anchoring much more difficult. Once the steel panels were welded together and brought to the trench, the construction site entered what many consider the backbone of the entire project, setting the wall panels, aligning them, and pouring concrete to lock them in place. This step determines how straight, strong, and long-lasting the nearly 1,130-mile barrier will be. First, large mobile cranes or truck-mounted cranes slowly lift each panel, which can weigh hundreds of kilograms, off the ground. Because each panel is almost 9 meters, about 30 feet, tall and long, like a giant sail, even a strong gust of wind can make it sway dangerously. That's why 2 to 3 workers on the ground always hold guide ropes, working closely with the crane operator to position the panel correctly over the trench. Once the panel is lowered into the trench, engineers begin the most critical task: alignment. They use laser levels, spirit levels, tension guidelines, and their own experience to make sure each panel stands perfectly vertical and lines up correctly along the wall's path. Even a small tilt of a few degrees can cause gaps, bending, or a crooked wall, which would weaken the structure and ruin its appearance. After the panel is in the exact position, workers temporarily weld its base to steel anchors or support frames already placed in the trench. These welds hold the panel steady while it waits for the concrete, preventing it from tipping over due to wind or accidental impacts. Right after that, a concrete mixer truck or a concrete pump moves to the edge of the trench. Fresh concrete is poured directly around the base of the panel, filling all the empty space between the steel and the soil. Workers use tamping rods or vibrating tools to remove air bubbles, helping the concrete press tightly against every surface of the steel post and form a solid bond. As the concrete hardens, it acts like a hidden anchor, locking the bottom of the panel firmly into the ground. This greatly increases its resistance to pulling forces, vibration, and attempts to break or pry it loose. In some important areas, such as near roads or places with soft ground, the crews don't just pour concrete around the base of the panels. They also add an extra concrete layer that extends about 5 feet outward from the wall. This creates a wider foundation pad that helps spread the weight and prevents the soil from eroding or sinking over time, especially after heavy rain. At the same time, this wider concrete base makes it much harder for anyone to dig under the wall. Instead of going through loose soil, someone trying to cross would first have to break through a thick layer of concrete before reaching the steel posts, making the job extremely difficult and time-consuming. After the steel panels were set in place and temporarily secured, workers used high-pressure water hoses to clean the entire surface. This washing step removes dirt, sand, mud, oil, and especially welding slag and metal fragments left over from the welding process. If these materials stay on the surface, the paint will not stick properly. The high-pressure water is sprayed from top to bottom, moving along each panel to make sure the surface is completely clean and no residue is left behind. Workers carefully follow the direction of the panels so water and debris don't build up in corners or gaps. Thanks to this cleaning step, the anti-rust coating and protective paint, applied later, can stick evenly and firmly. This greatly improves the wall's durability and corrosion resistance, which is extremely important in the harsh desert environment. At this point, the wall is almost complete, but one more layer of protection is added on top. Normally, the installation of razor wire, the sharp coiled blade wire you often see on high-security fences, is not done by civilian workers. Instead, it's handled by the military or border patrol units because of the high risk and security requirements. Razor wire has edges as sharp as a razor blade and is designed to cause deep cuts if someone touches it, making climbing over the wall almost impossible. The coils are lifted into place by specialized equipment or installed by hand, depending on the location. Soldiers then secure the wire using metal brackets and anchor hooks, making sure it stays tight and cannot be moved or pulled aside. With this extra protection added by the military, the top of the barrier becomes nearly impossible to climb with bare hands, greatly increasing the wall's ability to stop crossings. After many years of construction, hundreds of new miles of border fencing have been completed, helping reduce the number of easy crossing points and allowing Border Patrol to control the border more effectively. According to estimates from U.S. Customs and Border Protection, the total cost of the wall and related infrastructure has exceeded 15 billion USD, including materials, transportation, surveillance technology, and labor. However, that number is still growing because maintenance and repairs continue to cost hundreds of millions of dollars every year. Even though the wall slows down and spreads out illegal crossings, cartels have still found ways to get around it. The construction has also raised concerns about environmental impacts, especially on the desert ecosystem and the Rio Grande River region. Many experts argue that the wall affects wildlife movement and natural water flow. So while the border wall has provided certain benefits, it is far from a perfect barrier, and the struggle along the border continues. America built a barrier to keep people out, but Japan had to stop something much more powerful. Japan is facing the terrifying power of tsunamis. After suffering some of the most devastating tsunamis in modern history, Japan built one of the largest coastal defenses on Earth, massive sea walls that stretch hundreds of miles along its coast. These towering barriers weren't designed to keep people out. They were built to stop walls of water that could rise higher than buildings and destroy entire towns in minutes. The 2011 tsunami caused great loss to Japan, so the country built nearly 250 miles of tsunami defense walls, each 50 feet tall, with foundations plunging 80 feet deep, a concrete Great Wall designed to buy precious minutes for people to evacuate before the waves arrive. More than 12 billion USD was invested not only in building the walls, but also in upgrading emergency alerts and evacuation routes. The nearly 400-kilometer stretch runs along the Tohoku coastline in northeastern Japan, the region that took the full force of the 2011 tsunami. It extends continuously through the prefectures of Aomori, Iwate, Miyagi, and Fukushima, forming the longest and most unified coastal defense line in Japan's history. Once the exact route was finalized, crews began clearing the area, removing old houses, damaged infrastructure, power lines, and pipelines. At the same time, they built access roads, material yards, crane platforms, concrete mixing stations, and temporary drainage systems so construction could continue even during the rainy season. Much of the Tohoku coastline sits on weak sandy soil, so engineers first drilled detailed surveys and reinforced the ground. They installed deep concrete or steel piles, added layers of crushed stone and compacted sand, and stabilized the surface. The goal was to create a solid base strong enough to support a wall tens of meters tall without sinking, sliding, or cracking over time. Once the soil was stabilized, excavators dug massive foundation pits, in some sections going more than 20 meters deep. Near the shoreline, crews built temporary retaining walls or cofferdams to keep seawater out. After that, a base layer of concrete was poured, followed by dense steel reinforcement cages and large foundation blocks that formed an extremely heavy and wide foot to prevent the wall from being pushed over by powerful waves. Above the foundation, workers assembled tall, thick rebar cages based on the optimized lab design. Formwork was set in place, and concrete was pumped into the mold section by section. Each block, usually several dozen meters long, was poured, cured, inspected, and then connected to the next, creating one continuous barrier along the coast. On the ocean-facing side, crews installed special concrete units such as tetrapods, dolas, and other energy-dissipating blocks. These were stacked in multiple layers around the base of the wall to break the wave's force before it hit the structure. Some sections also used stepped faces, sloped surfaces, or splash reduction ledges to lower the height of water surges. On the landward side, soil and crushed rock were added along with drainage channels to prevent rainwater from pooling behind the wall. Many stretches include a walkway or inspection road on top, and in some towns the seawall even doubles as part of the local roadway. Railings, fences, safety ladders, and signage were added to allow safe public access. In some sections where the seawall needed extra thickness and impact resistance, crews added a layer of precast concrete blocks onto the outer surface. These interlocking panels were lifted into place by crane and arranged in a tight, uniform pattern to strengthen the wall and reduce erosion from constant wave action. Once secured, the tiles created a reinforced armor layer that helped the seawall withstand decades of pounding from the Pacific Ocean. So you've just explored the full process behind two of the largest walls ever built. Whether it's the massive U.S. border wall or Japan's towering tsunami barriers, both represent humanity's determination to protect itself against the greatest threats we face. Keep following Mandarin Tech for more fascinating insights.